Let's solve some problems from calculus about a hard topic called implicit differentiation. We'll think about it first with a relatively simple example where we have the unit circle with equation x squared plus y squared equals 1. We're going to consider the point whose coordinates x, y are 1/2 comma square root of 3 over 2 that is on the unit circle. Part A says to solve for y as a function of x for the upper half of the unit circle, call it f of x, and then we'll use that function to find the slope of the unit circle at the given point. Let's do that first. The rest of the problem is about implicit differentiation. So take the equation x squared plus y squared equals 1. We want to solve that for y. So first subtract x squared from both sides to get y squared equals 1 minus x squared. And then solve for y. In general, y would be plus or minus square root of 1 minus x squared. But because we want the upper half of the unit circle, the second coordinate of the point there is positive, we will take the positive square root. Y will be the square root of 1 minus x squared, or if you prefer, 1 minus x squared all to the 1/2 power. That will be our function f of x. Now we want to differentiate that to be able to find the slope of the unit circle at that point. So go ahead and do that. F prime of x. Think about this. We need the chain rule. We've got an inside function, 1 minus x squared, and we've got an outside function, x to the 1/2 power. The chain rule says take the derivative of the outside function, x to the 1/2 power, to get 1/2 x to the negative 1/2 power, but replace x with the inside function, which is 1 minus x squared. So we get 1/2 times 1 minus x squared to the negative 1/2, and then don't forget, multiply by the derivative of the inside function. The derivative of 1 minus x squared is negative 2x. And then we can simplify that. We can cancel the 2's. We can write this as negative x over, since that's a negative 1/2 power, it can go as a square root in the bottom. Negative x over square root of 1 minus x squared. Now we want to find the slope of the unit circle at that point. Now plug in that x coordinate of 1/2. So f prime of 1/2 will be negative. We can put a 1/2 up here. Square root of 1 minus 1/2 squared. 1/2 squared is 1/4. So this becomes negative 1/2 over square root of 3/4, right? 1 is 4 over 4. 4 over 4 minus 1 over 4 is 3 over 4. And then the square root of 3/4 is the square root of 3 divided by the square root of 4. The square root of 4 is 2. This becomes negative 1/2 over square root of 3 over 2. The 2's divide out. Ultimately, this simplifies to negative 1 over the square root of 3. That is the answer for the slope of the unit circle at this point. What is that value there? Let's approximate it. Negative 1 divided by square root of 3. It's approximately negative 0.577. Let's just draw a rough picture to see if it seems approximately right. The unit circle is this, centered at the origin with a radius of 1. So this would be 1 here, negative 1 there, negative 1 down here. The point has coordinates 1/2 square root of 3 over 2. Square root of 3 over 2 is, I think, 0.866. I better double check that just to make sure. Square root of 3 divided by 2 is 0.866. So it's a point that would be right about here or so. There's 1/2 right there. There is 1/2 square root of 3 over 2. We've just found the slope of the curve at that point, the slope of its tangent line. The tangent line would look about like this. You can certainly see that the slope is negative, and it doesn't look super steep. Certainly something between -1 and 0 seems reasonable. All right, that is not an implicit differentiation problem so far. It's when we start talking about parts B and beyond that we think about this new idea of implicit differentiation. Part B says assume. That is important with implicit differentiation, that we make an assumption that y equals f of x, that y depends on x, and without using the formula for f of x from part A, we're pretending we haven't done part A, find the slope of the unit circle at the given point. And you say, huh? How can we possibly find the slope of the unit circle at the given point if we don't use the formula for f of x like we did in part A? That's what implicit differentiation is all about. we're going to go ahead and find this derivative without actually using the formula for the derivative as we did in part A. So that begs a question, how in the world do we do that? Well, what you want to do is you want to, in the equation up here, the unit circle equation, replace the y with the function f of x. So instead of writing x squared plus y squared equals 1, I write x squared plus f of x squared equals 1. I'm replacing y with a function f of x that I'm assuming exists. I do know it exists, and in fact I know what it is. It's this function right there, but I'm pretending that I don't for the purpose of doing harder problems where you can't actually find f of x. This will apply to harder problems, as we will do after this problem. Take this equation and solve it for f prime. How? I don't see an f prime anywhere. Well, differentiate both sides. That's how to get an f prime in there. Take the derivative of both sides of this equation with respect to x. The derivative of x squared is 2x. The derivative of this is the trickiest part, I need the chain rule for. And I can write it symbolically, even though I don't know what f of x is, and even though I'm pretending I don't know what f prime of x is either. I'm pretending I don't know both. How? F of x is the inside function, x squared is the outside function. I need the chain rule. The derivative of x squared is 2x, so I get 2 times the inside function, f of x gets replaced. You replace x with f of x. Then the chain rule says multiply times the derivative of the inside function, f prime of x. And on the right side, if I differentiate a constant, I get 0. This is now an algebra equation I can pretty easily solve for f prime of x. It's linear in the unknown function f prime of x. Of course, if I solve for f prime of x, there will be an f of x on the other side, but that's okay. Don't worry about it. So I can subtract 2x from both sides and get 2f of x. F prime of x is minus 2x. Then I can solve for f prime of x by dividing both sides by 2f of x, so that it'll cancel on the left. F prime of x will be negative 2x over 2f of x. The 2's divide out. And moreover, I can also replace the f of x with y. And after all, I replaced y with f of x back here. The 2's will divide out. I can write this as negative x over y. And now I can plug in the given point into that expression and find the slope without ever having solved for f of x or f prime of x explicitly in terms of a function formula. So f prime of 1/2, we're going to get the same answer here, is going to be negative x, x is 1/2 at this point, over y. Y is square root of 3 over 2. And once again, this simplifies to negative 1 over the square root of 3. We get the exact same answer, and we never solved for the explicit formula for f of x. We never solved for the explicit formula of f prime of x. We assumed that the equation defined y as a function of x implicitly. There's something called the implicit function theorem that behind the scenes we're kind of using without explicitly saying, pun intended. We're assuming that that works, and then we're differentiating and solving for what we want to find, and it does work. It works ultimately as long as you don't divide by 0 in these kinds of problems, but we will think about what happens if you do divide by 0 in one of these problems that we do in this video. All right, what different can we do here in parts C and D? In part C, we're going to do part B again, but using Leibniz notation for the derivative, dy dx. I'll also use y prime, instead of writing f of x or f prime of x. Why? Because it's traditional to do it this way. Part C is the traditional way to do it, okay? But it's perhaps confusing, and that's why I did parts A and B first, is to help explain part C. I'm not even going to bother replacing y with f of x as I did in part B. I'm just going to look at this and in my mind say y is a function of x. And when I differentiate this with respect to x, the derivative of y squared is not 0 because y depends on x in my mind. Okay, that's really important. Now I differentiate this with respect to x, 2x plus, not 0, but 2y dy dx. I used the chain rule. I did the exact same thing that I did right there. These two things match. Thinking of y as a function of x, the outside function is the squaring function, the inside function is y. Or if you prefer, y equals f of x. Y depends on x, so the chain rule gives 2y times the derivative of the inside function, dy dx, which I can also write as a y prime if you want to save time. The right-hand side still differentiates to 0. You can still ultimately solve for y prime or dy dx in the same way. Subtract 2x from both sides, then divide both sides by 2y. The 2's cancel. You get negative x over y again. And once again, the final answer becomes negative 1 over square root of 3 when I substitute in the 0.1/2 square root of 3 over 2. I'm not bothering to use the vertical line notation for evaluate at, but you probably should. I'm trying to save a little time here. Okay, so I get the same answer as before. Part D. For fun, we're going to find the second derivative, y double prime. In Leibniz notation, the second derivative of y with respect to x twice, f double prime of x, at the given point using implicit differentiation. Now I could also differentiate that with the quotient rule, low d high minus high d low over the square of what's below, and I would encourage you to do so and confirm that you get the same answer, but to save time and to emphasize that this video is about implicit differentiation, let's do it with implicit differentiation, and let's use part C's answer for y prime in terms of x and y. Assuming, once again, y depends on x, y is a function of x, a differentiable function of x, and in fact a twice differentiable function of x, differentiate both sides of this with respect to x. I also could differentiate both sides of this. Maybe we should do it that way, just for fun. Okay, so this equation is 2x plus 2y, y prime equals 0. I could differentiate this one with the quotient rule, but if I differentiate both sides of this one with respect to x, I can avoid the quotient rule, so that's got a little bit of benefit. So differentiate with respect to x, the derivative of 2x with respect to x is 2. All right, let's use the product rule here. Differentiate this with respect to x. Be really, really careful. Y and y prime both depend on x. The first function is 2y, the second function is y prime. The product rule says take the derivative of the first function. The derivative of 2y with respect to x is 2y prime. Multiply times the second function, you get another y prime. Add the first function times the derivative of the second. The derivative of y prime is y double prime. Derivative of 0 is still 0. This can be also written as 2y prime quantity squared, if you prefer. And the goal now is to solve this equation for y double prime. Okay? It's a linear equation in y double prime that's very easy to do. I'd subtract 2 from both sides. I'd subtract this 2y prime squared from both sides, and then divide both sides by 2y. All the 2's are going to cancel. You're going to end up with y double prime equals, if I'm careful here, negative 1 minus y prime squared over, all the 2's cancel, over y, it looks like. And now we're going to evaluate this at the given point, x comma y equals, I'm using evaluate notation here now, 1/2 square root of 3 over 2. You don't see any x's in here, so I'm not going to plug in 1/2 anywhere, but I will plug in the fact that y prime is negative 1 over root 3 over, at this given point where x is 1/2 into this. So I'll get negative 1 minus y prime squared. There's y prime, plug that in. Negative 1 over root 3 quantity squared, all divided by y square root of 3 over 2. So it's kind of a nasty looking fraction, but it's technically doable here. We can simplify a little bit. If we square this thing, the negative sign there goes away, but there's a negative sign there, so we'll get 1/3 over square root of 3 over 2, which becomes 2 over square root of 3 times negative 4/3, it looks like, and that's negative 8 over 3 root 3. That is the correct exact answer for y double prime. You could also approximate what it is. I won't bother doing that. In number 2, we do have a curve, a cubic curve, whose equation is a bit more complicated. It does involve an x cubed. It also involves a cubic term with x squared times y right there. Technically, we still could solve this for y as a function of x because it's only quadratic in y, and we could ultimately use the quadratic formula. However, well, you could check it that way. However, I want to focus just on implicit differentiation. The graph of this curve is shown below. It's kind of a pretty looking curve. You can see it in blue here. It's got two pieces to it, a piece right there and a piece down there. But wait a minute, doesn't that fail the vertical line test? Well, so does the graph of the unit circle, and we didn't let that bother us. This is not the graph of just one function. It's the graph of two functions effectively put together from one equation. And that makes some sense if you think about it. If you did solve for y as a function of x, ultimately by getting 0 on one side and using the quadratic formula, you would have a plus or minus. Evidently, to get the curve that's the higher one, you'd have to probably take the plus one. Yeah, that would be the case. All right. I also have the point 1, 2 that's on the curve that you see here. I did draw its tangent line. Our goal in this problem is to use implicit differentiation to find the equation of this tangent line at that point, and also ultimately use that equation of the tangent line to estimate another point on the curve. All right, so let's go ahead and in part A, first of all, confirm that this is a point on the curve. That really is important to do. You could use implicit differentiation and try to solve for the derivative and plug in a point, but it could be nonsense because that point might not be on the curve. To really truly use this accurately, we want to first make sure the point is on the curve. How do you verify that? It's just algebra. Plug in x equals 1 and y equals 2 into both sides of this equation and see if you get the same thing. If you plug it into the left-hand side, you get 1 cubed plus 5 times 1 squared times 2 plus 2 times 2 squared. That becomes 1 plus 10 plus 8 is 19. And if you plug in y equals 2 on the right side of the equation, you get 4 times 2 plus 11 is 8 plus 11 is 19. The fact that those match makes us happy. That is enough to verify that this point with coordinates 1, 2 is on this curve, and it is this point that you see right here, 1, 2. Part B, use implicit differentiation to find the equation of the tangent line to the curve at that point. So, the derivative gives you the slope. If I use implicit differentiation, it's going to give me the slope of the tangent line. I also know a point on the line, 1, 2. That'll give me the equation of the line, and we'll also write it ultimately in slope-intercept form. So let's use implicit differentiation. We won't replace y with f of x. We won't try to solve for y as a function of x. We will just take this equation, and again, in our minds, we will imagine y to be a function of x. And so the derivative of y with respect to x is not 0, it's dy dx, it's y prime. The derivative of x cubed with respect to x is 3x squared. So now I'm differentiating. Careful on the next one, use the product rule. I've got a first function, 5x squared, and a second function, y. The derivative of the first, 5x squared, is 10x times the second function plus the first function, 5x squared, times the derivative of the second. Maybe your teacher wants you to write dy dx. I will just write y prime. It saves a little time. And then with this one, we need the chain rule. 2y squared. The inside function is y itself. You could replace it with f of x if that's less confusing. The outside function is 2 times something squared. So take the derivative of the outside function. 2 times something squared would be 4 times that something, but replace the something with the inside function, which is y. You could write it as f of x, times the derivative of that inside function, dy dx, or just y prime. On the right side, differentiate that with respect to x, you get 4y prime plus 0. Okay, solve this now for y prime. It's not as hard as it looks. It's linear in y prime. I can get all the y primes on the left side and everything else on the right. So let's see, and factor out a y prime, I'll get 5x squared plus 4y, careful, minus 4 from this term that's switched over to the right. I'm subtracting 4y prime from both sides. And on the right, I'll subtract 3x squared to get negative 3x squared, and I'll subtract minus 10xy. And now just divide both sides by 5x squared plus 4y minus 4. So y prime is going to be, in general, negative 3x squared minus 10xy all over 5x squared plus 4y minus 4. Technically speaking, we could use this to figure out a formula for f prime of x if we figured out a formula for f of x. Again, we could solve this equation for y as a function of x, ultimately using the quadratic formula. If this were cubic and y or fourth degree, it would be much, much harder to do so. And if you replaced the y here and here with that function f of x and simplified, you'd get a formula for the derivative f prime of x. You might imagine it would be probably pretty complicated. This is an easier way to go. Implicit differentiation is a nice problem-solving tool. We want to evaluate this at the point xy equals 1, 2. If I were using Leibniz notation, I'd put a vertical line here, and I'd emphasize x comma y is 1 comma 2. Replace x with 1 and y with 2. You don't have to solve for y as a function of x. So I get negative 3 times 1 squared minus 10 times 1 times 2 over 5 times 1 squared plus 4 times 2 minus 4. Looks like we get a negative 23 on the top. And on the bottom, we got a 5 plus 8 is 13, minus 4 is 9. Yes, this is the correct answer for the slope. Now we need the equation of the tangent line. Tangent line. You could give it a function name if you like. I think I will, actually. Y equals L of x, L for line. You could maybe call it T of x, T for tangent. Or L could stand for linear as well, line or linear. It's the second coordinate of the point. It's f of 1, if you like, which is 2. 2 plus the slope, which is negative 23 over 9, times x minus the first coordinate of the point, which was 1. So this becomes, if you simplify it, multiply that through, negative 23 over 9x plus 23 over 9, then plus 2. In slope-intercept form, it's y equals negative 23 over 9x. 2 is 18 over 9, so it looks like we get plus 41 over 9. But to tell you the truth, to approximate the function at x equals 1.4, as we will do in part C here, it's actually a little easier to use this form of the equation instead of that form. I mean, it's not hard using that form either, but when you replace x with 1.4 here, this is very easy to compute. So it's maybe a little quicker, especially, and can even be done in your mind sometimes if this slope were simpler. That's what we're going to do in part C. Part C says, use the answer for part B to estimate, not exact, the point on the cubic curve whose x-coordinate is 1.4. And based on the picture, is the estimate too large or too small? You can see from this picture, when x is 1.4, it looks like the tangent line is underneath the curve, so the tangent line approximation, the linear approximation, is going to be too small. Actually, it does look like this point is near an inflection point, and you could try computing y double prime to see if it is. I think it's not, actually, but you could try it on your own. I think it's slightly negative second derivative here, and definitely negative second derivative over here. This tangent line is below the curve. We'll get an answer that's too small. But what is the answer for part C here? F of 1.4, if I want to give the function a name, f is approximately L of 1.4, and that'll be 2 minus 23 over 9 times 1.4 minus 1, and that is, of course, 0.4. Sorry about that, that wasn't on the screen there. And now we'll just go ahead and use the technology. So we get 23 over 9 is this, 2.5 repeating, times 0.4 is this, and that's what I have to subtract from 2. So I get about 0.9, I get 0.97 repeating. Let's just approximate it to 0.98, and it's going to be too small again. Let's see if it seems reasonable looking at the picture. 1.4 is right about here. We just approximated the second coordinate of the point on the red line to be slightly less than 1. Yeah, it looks reasonable. The corresponding point on the blue curve itself is slightly higher. Is it bigger than 1? Maybe. It's hard to tell exactly at this level of resolution for the picture. you can see that the curve for number 3 is a beautiful curve. The equation sine of xy equals x defines the beautiful curve that you see here in blue. Wow, is it really that? Yes, it really does look like that. And in part A, we want to confirm, first of all, that this point, whose coordinates are 1/2 comma pi over 3, is a point on the curve. That's the black point that you see here. And in part B, we're going to use implicit differentiation to find the slope of the curve, of the tangent line to the curve. The scales on these axes are not the same, so it's a little hard to eyeball the slope other than to say it's positive here. And, we're finding it at this point on the curve, and we could solve this for y as a function of x, but I will tell you that if you do solve for y as a function of x and graph that corresponding function, you only get a very small piece of this overall curve. And we could try to make the problem harder, so to speak, by solving for the slope at some other point on this curve where solving for y as a function of x is not helpful. I'll go ahead and do that right now. If I take the inverse sine of both sides, I could write xy is inverse sine of x. And then I could say y is inverse sine of x over x, or if you prefer, arc sine of x over x. However, if you graph that function of x, you will only get this little piece of the curve that's down at the bottom. You could still solve the problem with it, but you would not be able to solve problems involving other pieces of the curve. Anyway, let's go ahead and do implicit differentiation here. So we have, in part A, we need to confirm it's on the curve. So we need to plug the point into both sides of the equation. First of all, on the left side, sine of xy is sine of 1/2 times pi over 3. That is sine of pi over 6. Let's assume these things are in radians. Sine of pi over 6 is 1/2, and that does equal x. Okay, that's sine of xy. Ends up equaling 1/2. That does equal the x coordinate. Yes, this point is on the curve. Pi over 3 is a little bit bigger than 1, and the first coordinate there is 1/2, which looks about right. Now in part B, let's do implicit differentiation after we've confirmed the point is on the curve. Like I mentioned in number 2, you do want to confirm the point is on the curve first if you are able to. Use implicit differentiation to just find the slope this time. We won't bother finding the equation of the tangent line at this point. Okay, now we got the sine function in there. Well, okay. Before I differentiate this with implicit differentiation, let's imagine what would happen if I replaced y with f of x. If I use that notation, I'd have sine of x times f of x. It would be a chain rule problem where the inside function would be x times f of x and the outside function would be the sine function. I could differentiate the outside, cosine of x, but then plug in the inside function, which is x times f of x, and then differentiate that inside function, x times f of x, with respect to x with the product rule. I am going to do that here, but I'm not going to write f of x. As traditional, I'm just going to keep it as a y. But in your mind, remember, y is a function of x. So the equation sine of xy equals x. Of course, the derivative of the right side is easy. It's just 1. If I differentiate with respect to x, I'll write a ddx symbol there, even though I haven't done that so far. I need the chain rule. The derivative of the outside function, sine, is cosine. Plug in the inside function, which is x times y. Then multiply times the derivative of that inside function using the product rule, remembering I'm assuming y is a function of x. So I've got a first and second function. The derivative of x with respect to x is just 1 times the second function, plus the first function x times the derivative of the second, dy dx, or for short, y prime, equals the derivative of the right side with respect to x, which is just 1. Solve this for y prime. Do algebra. I can say y plus xy prime is 1 over cosine of xy, which I could write as secant of xy, but I don't have to. Subtract y from both sides. X times y prime is 1 over cosine of xy minus y. I could subtract these fractions by getting a common denominator of cosine xy, but I think I'll just divide both sides by x now. And I'll write y prime as 1 over cosine of xy minus y, all divided by x. You could multiply the top and the bottom by cosine of xy. Is that worth doing? Not necessarily worth doing. Now we want to evaluate this at the given point. The given point has coordinates 1/2 pi over 3, so I could use this notation. If I were using Leibniz notation, I could do this. And in this equation here, I will replace every x with a 1/2 and every y with a pi over 3. I'll get 1/2, 1 over cosine of, the product of those two things is pi over 6, minus y, which is pi over 3, all divided by x, which is 1/2. Simplify a little bit. Dividing by a half is the same as multiplying by 2. Cosine of pi over 6 is square root of 3 over 2. We've got a pi over 3. Multiply the 2 through. Dividing by square root of 3 over 2 is the same as multiplying by 2 over square root of 3. 2 times 2 is 4. I get 4 over square root of 3 here, it looks like, minus 2 pi over 3. And then we could get a common denominator of 3 root 3. And ultimately get 12 minus 2 pi root 3 all over 3 root 3. Okay, so I did that simplification pretty fast. I hope I didn't make a mistake. Actually, I know what the approximate answer is. So let's go ahead and see if I got the right approximate answer. It's like 0.255 or something like that. Let's just double check this here. 12 minus 2 pi times the square root of 3. And then all divided by 3 root 3, which is the same as 3 to the 1.5 power. 2.15. Okay, about 2.15. I thought it was 0.215. I thought it was 0.255. Let's see, do I have the answer somewhere in my computer? Double check this answer. Yes, okay, this is right. About 0.215. That's correct. That's the slope. Our last problem involves a quadratic equation, but more complicated than number 1. And in fact, this curve is going to be a circle, the curve defined by that thing. And in part A, we're not doing any calculus. We're going to get a little practice with the method of completing the square to find the center and the radius of the circle. And in fact, in part B, we're also not going to use any calculus. We're going to figure out, based on that, where the tangent line to this circle is both horizontal and vertical. It's in part C where we'll use calculus to try to confirm the answer to part B using implicit differentiation, and we'll also need the quadratic formula. Okay, so how do you confirm this curve is a circle? Well, let's rearrange the left side first. Let's group the x terms together, and then we'll group the y terms together. And we'd ultimately like to complete the square, because we'd ultimately like to write this as x plus or minus something squared and y plus or minus something quantity squared equals something squared. That's the equation of a general circle. And for the method of completing the square, you look at the coefficient of the linear term, in this case -4 for the x, divide it by 2 to get -2, and then square that number. -2 squared is +4. Go ahead and add 4 there. Of course, you can't just add 4 willy-nilly. You have to compensate by adding 4 on the other side too. Do the same kind of thing for y. Its coefficient for the linear term is 7. 7 divided by 2 is 7/2. 7/2 squared is 49/4. So we got some fractions. Okay, we can handle it. And I got to add that on the other side too. Okay, so this is not super simple. We're dealing with fractions here. These two now become perfect squares. That's the magic of completing the square. This becomes x minus 2 quantity squared. This one becomes y plus 7/2 quantity squared. The right side, I need to get a common denominator of 4. This is a 19 here. 19 is the same as 76 over 4 plus 49 over 4. We're going to get 125 over 4, which is the same as, well, square root of 125 over 2 quantity squared. Square root of 125 is the same as square root of 25 times square root of 5, which is 5 root 5. So it looks like the radius of this circle is going to be 5 root 5 over 2. That's the quantity that's squared. And the center of the circle is going to be at the point with coordinates 2, -7/2, 2, -3.5, it looks like. So this circle, if I was going to sketch it quickly here, center is at x equals 2, y equals -3.5. So let's see, that'd be right about here is the center of the circle. What is 5 root 5 over 2? What is the radius? 5 to the 1.5 power divided by 2. The radius is about 5.59. This thing right there is approximately 5.59. So if I'm going to try to draw this semi-accurately here, 4, 5, 6, okay, I'm going to run out of room here. Let's see, a radius of about 5.59, 2, 3, 4, 5, somewhere about like this. 1, 2, 3, 4, 5, somewhere, yeah, something about like this is the graph. I'm not drawing it very nicely because I'm trying to save time and go quickly, and I ran out of space. All right, so that's basically what the circle looks like. As far as part B goes now, we found the center and the radius. Use part A to find the points where the tangent line is horizontal and vertical. Okay, it's going to be horizontal up here and also down there at points whose first coordinates are the same as the center, 2, and whose second coordinates are going to be something else. And it's going to be vertical at points whose second coordinate is -7/2, -3.5, and whose x-coordinates need to be found. To find this point, for example, replace x with 2 and solve for y. I could replace x with 2 up here and solve for y using the quadratic formula. I could also replace x with 2 here and solve for y. That's probably a little quicker. If x is 2, I get 2 minus 2 is 0, 0 squared 0. I get y plus 7/2 squared equals 125 over 4. Take the plus or minus square root of both sides. Then subtract 7/2. You get y is -7/2 plus or minus the square root of this, which would be 5 root 5 over 2. So that'd be -7 plus or minus 5 root 5 all over 2. Those would be the y coordinates of this point here and the point that would be down there, where the tangent is horizontal. Where the tangent is vertical, you'd want to replace y with -7/2. Again, I could do that in the original equation and use the quadratic formula. I guess that, did I make that part of the directions there? I was sort of making it part of the directions for C, but I could have done it for part B as well. Y equals -7/2. Plug that in here. Get x minus 2 quantity squared is 125 over 4. And then solve for x. You're going to get x is ultimately 2 plus or minus 5 root 5 over 4, over 2, excuse me. And that can also be written as 4 plus or minus 5 root 5 all over 2. Okay, and we can approximate what those are. Those would be the first coordinates of these 2 points. All right, let's confirm the answers. Confirm the answers with implicit differentiation and the quadratic formula. We'll see if the quadratic formula is really necessary, or maybe I can already use what I did in part B here. So this is now part C. This blue was part B, and the green was part A. Part C, we want to use implicit differentiation. X squared plus y squared minus 4x plus 7y equals 15 was the equation. We're trying to find the slope, and where the slope is 0, that's where the tangent is going to be horizontal. And where the slope is infinite, yeah, infinite, where we'd be dividing by 0, that would be where the tangent line is vertical. Differentiate with respect to x, get 2x plus, careful, not 0, but 2y, y prime, with the chain rule. Then differentiate minus 4x, get minus 4, and then the derivative of 7y with respect to x is 7y prime. 15 is an honest-to-goodness constant. Its derivative is 0. Solve this equation for y prime. The couple steps, what you'll get is 4 minus 2x all over 2y plus 7. If these two terms involve a y prime, you can factor the y prime out and get a 2y plus 7 in parentheses times y prime. You bring these terms over to the other side, you get this. Yeah, okay, so that is y prime, and we can use it to find slopes. When is it 0? If I set this equal to 0, it's 0 when 4 minus 2x is 0. In other words, when x is 2. And I won't bore you by refining out y in that case. I'll just refer back up to this case here to find the corresponding values of y. We do the same work. We could use the quadratic formula if we went back up here. I guess I'm not following my directions here. I would encourage you to try it. Try it with the quadratic formula. If I set this equal to infinity, can I do such a thing? Infinity is not a number. So this is a little bit fishy here. Well, okay, it does end up being that would be where you divide by 0 here. And where you'd be dividing by 0 there, you would not have a 0 up top. So we would not have a 0 over 0 situation. So let's see here. Yeah. Effectively, that's going to imply 2y plus 7 equals 0. So y equals negative 7/2. And then again, not to bore you with redoing things, you'd go back up and essentially do the same thing you did here, or go back up to the original equation, plug in y equals negative 7/2 here and here, get a quadratic in x that you could solve for x with the quadratic formula. And again, your answers are here in the first case and here in the second case. And again, you can approximate these numbers if that is helpful for you. Thanks for watching.